Okay, let's have a go at calculating this integral here. So we've got an integral of arcsine 1 over x squared minus 1 between root 2 and infinity. So the first thing I'm going to do towards calculating this is, when we've got an integral up to infinity, I know that this is defined as a limit. So the integral from root 2 to t, as t goes to infinity, of just the same integrand here. 1 over x squared minus 1, arcsine of that. And there's a few different approaches I could try at this point. I could try maybe substitution. So maybe try u equals 1 over x squared minus 1. However, what I'm going to actually do now is I'm going to use a integration by parts trick. Essentially what I'm going to do is, because I can see that this arcsine 1 over x squared minus 1, I know how to differentiate arcsine of any function using the chain rule. And basically that'll give me something quite nice. And even though I'm trying to integrate this, what I can do is, if I want to differentiate this to get a nice function out, what I can do is think of this as the integral of u times v dash respect to x. So I can set my u as arcsine 1 over x squared minus 1. My v dash is just 1. So obviously when I integrate v dash, I just get x. And then when I differentiate my u, what will I get here? So I'll use the chain rule. So let's differentiate the innermost function first. So if we differentiate 1 over x squared minus 1, you'll get 2x, and then minus 2x over x squared minus 1 all squared. And then we need to multiply this by the derivative of arcsine, where we leave the inner function alone. And when you differentiate arcsine, you'll get 1 over the square root of 1 minus your inner function squared. Okay. So then what we can do is we can rewrite this integral with the limit using integration by parts as. So again, let's keep the limit as t goes to infinity. Now we're going to have, so u times v, so x arcsine 1 over x squared minus 1. This is evaluated to t from root 2. So it's going to be the limit of this plus, well, now we're subtracting minus 2x over x squared minus 1 squared times this times x. So that gives us a plus, so it's minus minus 2x. We put this in the integral between 2 and t. So now we're going to have 2x over x squared minus 1 all squared multiplied by 1 over root 1 minus 1 over x squared minus 1 all squared. And then finally we multiply by an x as well. So I'll put that x in here, 2x squared dx. And this is the limit as t goes to infinity of all of this. So now we could work with the limit here. This thing's probably not too bad, but I think the next step, what we really need to do to solve this problem, is try and simplify this function here. So this is definitely a bit of a mess at the moment. Okay, so let's write it out again. Got 2x squared over x squared minus 1 all squared. And then we've got a square root of lots of nasty stuff here. So 1 minus 1 over x squared minus 1 all squared. So what I'll do is, let's first of all work with the square root. So if I rewrite this 1, what I'm going to do is I'll rewrite this as basically x squared minus 1 all squared over x squared minus 1 all squared, so that then we've got kind of two fractions over the same denominator. So everything else will stay just as it is for now, the 2x squared, the x squared minus 1 squared, and we will get, now we'll have x squared minus 1 all squared, and then minus 1 all over x squared minus 1 all squared. I'll make this square root a bit bigger. And this is actually quite nice already. You can see you can take out, outside of this square root, you can take out x squared minus 1 squared, and then this will cancel out one of your powers of x squared minus 1 here. And you know that you get the positive root because, remember, x is always bigger than root 2, so x squared minus 1 is always going to be positive. So just that one step gives us 2x squared now over x squared minus 1 into the square root of, now this is no longer a fraction, it's just x squared minus 1 all squared minus 1. When I expand this, I'll get a plus 1, which would cancel with that minus 1. So let's have a go at doing that, see what it gives us. So again, we'll leave everything else alone. 2x squared over x squared minus 1. And now we've got the square root of, when we expand this, we'll get x to the 4 minus 2 x squared plus 1 minus 1. Those two terms disappear, they cancel out with each other. And here we could take out this factor of x squared, which is common to both of these terms. Let's do that, see what it gives us. So now we've got 2x squared over x squared minus 1. And then we've got square root of x squared is just x. We know it's definitely equal to x rather than modulus of x because x is bigger than root 2. So this is always positive. And then we're starting to get something a bit more workable in the square root now. This is just x squared minus 2. And here this x is going to cancel with your x to the power of 2. So what we're left with now is 2x over x squared minus 1 into the square root of x squared minus 2. Okay, so that is equal to this entire integrand here. So now what we'll do is we'll replace this in the integrand, I'll clean the board, and then we'll have a go at calculating this integral, and then eventually we'll take the limit as t goes to infinity as well. Okay, so now to actually evaluate this integral, what I'm going to try is basically look at this and think, are there any nice substitutions that I could do that could help? And if you look at the square root of x squared minus 2 term here, this is actually quite nice because if you imagine you substitute u equals x squared minus 2 in the square root, then when you differentiate this with respect to x, you'll actually get a 2x term on top from differentiating the x squared using the chain rule, and then you'll get on the bottom root x squared minus 2. And of course you've got to multiply by half, which is your power of x squared minus 2 there. So this will cancel with this. But then this is still quite nice because then you can write du is equal to x over root x squared minus 2 dx, which is actually a significant chunk of what we've got in the integrand there. So quite a lot of this will disappear away. So we also need to write x squared minus 1 in terms of u. So what we can do is we can say u is equal to root x squared minus 2. Let's square both sides. U squared equals x squared minus 2. Then we need x squared minus 1, so just u squared plus 1 is equal to x squared minus 1. So then that's our x squared minus 1 term dealt with. So now we need to deal with this root 2 and t. So changing variables then from x to u. So when x is equal to root 2, u is going to be the square root of root 2 squared minus 2. So 2 minus 2 gives us 0. The square root of 0 is 0. And then when x is t, u is just going to be root t squared minus 2. Okay, so now we've still got this factor of 2 here, and this x squared minus 1, we know that this is equal to u squared plus 1. And then all of this stuff disappears, that just turns into du So now this is actually quite a nice integral. We know how to deal with this. This is an arctan integral. So this is going to be equal to 2 and then arctan root t squared minus 2 minus arctan of 0. So arctan of 0, this is just equal to 0. So what we're going to get here is 2 arctan of the square root of t squared minus 2 for our integral. Okay, so now let's combine this then with this term here, and then we'll take limits as t goes to infinity. So now let's substitute in our values of x when x is t and x equals root 2. So we'll have limit as t goes to infinity of now t arcsine 1 over t squared minus 1. So this term might be a little bit difficult to deal with. We've got something which converges to infinity, then this is going to be like arcsine of 0, which will go to 0. And then we subtract root 2 arcsine of 1 over root 2 squared minus 1, which is 1 over 2 minus 1, 1 over 1, which is 1. Okay, that's nice. And then we also have plus 2 arctan root t squared minus 2. So this middle term, this is nice, there's no dependence on t here. So basically this is going to be root 2 times arcsine of 1. Arcsine of 1 is pi over 2, so you'll have pi root 2 over 2 for this term. This term, 2 arctan root t squared minus 2, well, you know that as t goes to infinity, the square root of t squared minus 2 also goes to infinity. So arctan of all of this will converge to pi over 2, so arctan of positive infinity. So you'll get this converges to 2 pi over 2, which is just equal to pi. And then next we need to deal with this term here. And this one, this is slightly more complicated. What I'm going to do now is I'm going to write it in a slightly different form. So the limit as t goes to infinity, and basically because I've got something converging to infinity, something converging to 0, I'm going to see, because arcsine is quite difficult to deal with, but I know how to deal with its derivative, I'm going to see if I can't use L'Hopital's rule here. So basically I'll get, let's write this as arcsine 1 over t squared minus 1 divided by 1 over t. And then this will be this limit. Assuming this limit exists, we'll have minus pi root 2 over 2 plus pi. So you'll have plus pi 1 minus root 2 over 2. So here let's check that we can use L'Hopital's rule. So arcsine of 1 over t squared minus 1. This is going to be our arcsine of 0. So this thing definitely converges to 0. And then 1 over t, as t goes to infinity, this also converges to 0. So it's going to be okay to use L'Hopital's rule here. So let's have a go at differentiating arcsine of 1 over t squared minus 1. We'll differentiate 1 over t as well. So we have already actually seen how to differentiate arcsine 1 over t squared minus 1. This gives us big nasty expression minus 2t over t squared minus 1 squared, and then your big square root here of 1 minus 1 over t squared minus 1 all squared. And then we also know that this will simplify to root 2 over t squared minus 1, and then the square root of t squared minus 2. So that's the derivative of arcsine of 1 over t squared minus 1, and then the derivative of 1 over t, it's much easier, this is just minus 1 over t squared. So that means that our integral then, by L'Hopital's rule, is going to be this limit, so the limit as t goes to infinity now of the derivatives, so you have minus 2 over t squared minus 1 root t squared minus 2, and then this entire fraction here divided by minus 1 over t squared, of course plus pi into 1 minus root 2 over 2. So let's tidy this up a little bit here. Limits t goes to infinity of this fraction can be rewritten as, first of all, your negatives cancel, and then we can put this 1 over t squared, put a t squared on top of the fraction, so you'll get 2 t squared over t squared minus 1 to the square root of t squared minus 2. And then we still got to add pi into 1 minus root 2 over 2. So now let's calculate this. You might be able to see that this is going to go to 0, but just to make that really clear, I'll add in another step of working. So we'll get the limit as t goes to infinity of the same fraction, but now I'm going to divide the top and the bottom by t squared. So I'll get 2 over, now I get 1 minus 1 over t squared. And then the square root here just stays as it is because I've divided this term by t squared. So t squared minus 2 in the square root stays as it is, plus pi into 1 minus root 2 over 2. And then you can see here, numerator is just 2. This 1 minus 1 over t squared, this is just going to converge to 1 as t goes to infinity. But then this term here converges to infinity as t goes to infinity, so you'll get 2 over something which converges to infinity. So this whole limit is going to be equal to 0. So what are you left with? All you're left with then is this nice pi into 1 minus root 2 over 2 term. So we can conclude then that our integral between root 2 and infinity, arcsin 1 over x squared minus 1 respect to x, this is simply equal to pi to 1 minus root 2 over 2. And that's very nice, considering how complicated this got at some of the steps. Very nice answer there.